Welcome back, everyone. For the species given below, number 1, draw an appropriate Lewis structure. Number 2, draw a structure that shows approximate bond angles. And number 3, state if it has a net zero dipole moment. We're given the structure of HClO3, which is chloric acid. We're going to start with the first part where we want to actually want to draw an appropriate Lewis structure. We have 3 different atoms in the given structure, hydrogen, chlorine, and oxygen, which have 1, 7, and 6 valence electrons respectively, because those are the group A numbers that each atom belongs to. So the total number of valence electrons in the structure would be 1 valence electron from hydrogen, plus 7 from chlorine, plus 6 from each oxygen, so that would be 3 multiplied by 6. And if we calculate the result, we end up with 26 valence electrons. Our next step is to assign the central atom. We are choosing between chlorine and oxygen because they form more bonds than hydrogen. Hydrogen can only form 1 bond. Chlorine is less electronegative than oxygen, so it must be the terminal atom. I'm sorry, it must be the central atom, right? Since central atoms are less electronegative than terminal ones, so if oxygen is more electronegative, it will be the terminal atom. So we're going to assign 3 chlorine-oxygen bonds. We are always drawing single bonds to begin with. And the hydrogen atom must be bonded to one of the oxygen atoms. That's because if we have a structure of an acid, the hydrogen atom must be bonded to oxygen so that the bond is more polarized, and that makes sense, right? Whenever we have an oxo acid, hydrogen is always bonded to oxygen. Our next step is to satisfy the octet rule for the terminal atoms. So that means we are adding 3 lone pairs for 2 of our oxygen atoms to have 8 total, right? 2 from the bonds, and then 6 electrons from lone pairs. For the final oxygen atom, we only need to add 2 lone pairs because there are 2 bonds already, which provide for electrons. Now our next step is to calculate the total number of valence electrons assigned. So we have 8. Then we have our chlorine-oxygen bond, so that'll be 1, 2, 3, 4, 5, 6, 7, 8, so 8 more. 8 multiplied by 3 gives us 24, so we need 2 more electrons to have 26. And based on the rules, those 2 electrons must be placed onto our central atom, which is in this case chlorine. Well done. Our next step is to try to minimize the formal charges, but before we do so, we need to calculate them. So the formal charge of chlorine, according to the formula, we're using the number of valence electrons of chlorine. So chlorine has 7 valence electrons. We're subtracting the number of bonds, so we have 3 bonds, and the number of lone pair electrons, so that'd be 2. 7 minus 3 minus 2, that gives us a formal positive 2 charge on chlorine. For each oxygen, specifically for the first 2 oxygen atoms, we will have 6 valence electrons minus 1 bond minus 6 lone pair electrons. And that gives us a negative formal charge for oxygen. One of them, the other one, and of course the third oxygen has 2 bonds and 2 lone pairs, so it has no formal charge. And hydrogen also has no formal charge because it simply has 1 bond in its normal state. If we want to minimize the formal charges, we want to get rid of one of the lone pairs from the first oxygen and introduce a double bond. So now oxygen will have 2 lone pairs and 2 bonds. As a result, its new formal charge will be 0. So we're going to get rid of -1 and make it 0. And similarly, we want to minimize the formal charge of the other oxygen performing the same step. We will introduce a double bond out of its lone pair. And that's how we will end up with a formal charge of 0 for that oxygen. If we recalculate the formal charge of chlorine, it is now 0 as well, because 7 minus 5 bonds minus 2 lone pair electrons gives us a formal charge of 0. Well done, so we have our Lewis structure. Let's go ahead and draw it once again. So we have chlorine with a lone pair, 2 double bonded oxygen atoms. Each oxygen has 2 lone pairs. Then 1 single bonded oxygen that has hydrogen attached to it with 2 lone pairs. And that'd be our answer for the first part of the problem. We got the Lewis structure of chloric acid. Our next step is to predict the bond angles. And to do that, we are going to look at the previously drawn structure and understand how many electron regions there are on the central atom. So basically we have 1 chlorine-oxygen double bond, that's 1 electron region. Another one, that's 2 electron regions. Then we have a single chlorine-oxygen bond, that's the 3rd electron region. And we have a lone pair. So the number of electron regions is 4, which corresponds to an sp3 hybridized chlorine atom. And sp3 electronically corresponds to 109.5 degrees. But because instead of having a substituent, we actually have a lone pair, for each lone pair, we can estimate that we are subtracting 2.5 degrees to end up with an estimated value of 107 degrees. Right, because we have trigonal pyramidal geometry, similarly to what we see in ammonia. So the geometry is trigonal pyramidal. However, for the oxygen atom, because we have an additional bond angle, we also have 1, 2, 3, 4 electron regions, 2 bonds and 2 lone pairs. So that would also correspond to an sp3 hybridization, but because there are 2 lone pairs, if we want to predict the correct bond angle, we're going to take 109.5 degrees, and we're going to subtract 2.5 degrees multiplied by 2, which gives us 5 degrees, right? Because each lone pair squeezes our bond angle by roughly 2.5 degrees. So we have to subtract 5.0 degrees, and we end up with 104.5 degrees, which makes sense, right? The bond angle is very similar to the bond angle in water, which is 104.5 degrees. The geometry is bent, right? Because even though we have an sp3 hybridization, which electronically is tetrahedral, but due to the presence of 2 lone pairs, we have bent geometry for oxygen. Meaning we can draw the 3-dimensional structure now. So we have our chloro group. Actually, we have our central chlorine atom, double bonded to 2 oxygen atoms. We want to make sure that we draw a trigonal pyramidal geometry. That means one of the substituents, specifically our oxygen atom, is pointing away from the viewer, and that oxygen atom is bonded to hydrogen. Of course, we can add lone pairs. And neatly state the bond angles, starting with chlorine. We know that the geometry is trigonal pyramidal, and we have OClO bond angles. So those angles, oxygen, chlorine, oxygen bond angles, will be 107 degrees. In addition to that, we have OClO bond angle for our single bonded oxygen atoms. So the first one was between double bonded oxygen atoms, and now we have single bonded oxygen atoms. So OClO, one of the oxygen atoms is double bonded. That would also be 107 degrees because each of the angles is 107 degrees. Now, for the oxygen atom, which corresponds to the bent geometry, we said that the hydrogen-oxygen-chlorine bond, or HOCl, corresponds to 104.5 degrees. Well done, so we have predicted our bond angles, and we have drawn the three-dimensional representation of the structure. And finally, we are ready to answer the final question in this problem. What about the net dipole moment? We have to recall that the net dipole moment corresponds to the vector sum of the individual dipole moments. Each oxygen atom is more electronegative than chlorine. So to illustrate the concept, we're just going to redraw the structure once again. Because each oxygen atom is more electronegative, we will have one dipole moment from chlorine to oxygen, another one from chlorine to oxygen, the third one from chlorine to oxygen, and we also have a dipole moment from hydrogen to oxygen because oxygen is more electronegative. But there's also a lone pair which creates a dipole moment pointing upwards. The dipole moments do not cancel out due to multiple reasons. The lone pair is not an oxygen atom, so its dipole moment does not have the same magnitude as the dipole moment between chlorine and oxygen. So that's one of the reasons why the dipoles do not cancel out. And in addition to that, we have a comparison between single and double bonds. So that means for the third part, the net dipole moment mu is not equal to 0. And those will be our final answers. Thank you for watching, and I hope to see you in the next video.